Okay, so section number 2 is how to balance redox reactions using what is called the oxidation number method. So I left our rules for assigning oxidation numbers over there from the last lecture we did. And so you just remember how to do that, because every single time we do any of these other processes, the first step is always to assign oxidation numbers. Okay, so here are your rules, and again I've shortened them into smaller segments that are easier to remember than the ones listed in your book. Okay, but step 1 is always to assign oxidation numbers. So we got to go through this and give everybody an oxidation number. So it'll be a good review of these over here as well. So copper by itself must have a charge of 0, because that's an element in its natural state. There are no other elements in their natural state. Okay? Monatomic ions. The only ionic compound in here is really this copper nitrate. And if you remember that this nitrate has a -1 charge, like you memorize that from your list, then the only reason there's 2 of them is if this copper has a +2 charge. Okay? Rule 3, go through and get hydrogen out of the way. This is +1. These are +1. Okay? Rule 4, everyone else who's connected to someone else, give the most electronegative element what it wants. So for this substance, the oxygen is stronger than nitrogen, so they're -2. Same thing here, same thing here, same thing there. Okay, and now all that's left is number 5. Make sure everybody adds up to their charge. So we currently have -6 from the oxygens, +1 from the hydrogen, so we're at -5 right now, which means this nitrogen has to be +5. And over here, these nitrates, okay, they have to be -1 overall, so you have a -6 from the oxygen, which means the nitrogen's got to be +5. Okay. Over here, these oxygens are -2. That gives us -4. So this nitrogen must be +4. And we already finished that. So we are officially done with step 1. We have assigned everybody their oxidation numbers. Step 2. Identify the people being oxidized and the people being reduced. So right off the bat, I notice my copper is being oxidized. Okay, notice how we always connect them. Okay, and I notice that I wrote a 4 on that nitrogen. I did not write a 4 over here. So I'm going to bring this one over. And my nitrogens are being reduced. Everybody else is keeping their ionic charge. Okay, so we are now done with step 2. Step 3, how many electrons are being oxidized or reduced? This copper is being oxidized by 2 electrons. The nitrogen is being reduced by only 1 electron. Okay. So once we've got that, that's a problem, because the nitrogen is only taking 1 electron per atom, but the copper needs to give up 2 electrons. Okay, which is why we have to do step 4. We have to balance those electrons. So the way we do this is we say, okay, every nitrogen atom is reducing by 1 electron. So we're going to get to 2 atoms, which will actually give us 2 electrons that were being reduced. And the way we can do that is if we put a 2 here and a 2 there. Okay? But now we have balanced our redox reaction. So no matter what, we have to have two of those, one of those, and one of those. So now the trick becomes, how do we balance everybody else? So if you'll notice, we have two nitrates here that are both being reduced. But we also have two more nitrates that are not being reduced on the right-hand side, which means we need two more nitrates on the left-hand side, but these ones are not being reduced. So we can change that to a 4. And now we have coppers, nitrates, and nitrogen dioxides all balanced. The only thing that's not working right now is the waters, the hydrogens and the oxygens. Okay? But because everybody else is already balanced, we have 4 hydrogens here, which means we should be able to make 2 waters. And that should make sense because this substance came from a nitrate, which is NO3. So for every one of these that we made, we had 1 extra oxygen floating around somewhere. And so we have to have 2 waters because the water is where the leftover oxygen goes. And so now if we come back, we have 1 copper and 1 copper. We have 4 hydrogens, 4 hydrogens. We have 4 nitrogens. We have 2 nitrogens in this chemical and 2 more there, which gets us to 4. We have 12 oxygens on the left. We have 6 in the first chemical on the right, plus 4, plus 2 is 12. Okay? And you just have to go through this checklist every single time. And it's just a matter of how fast can you do it. Okay? So we're going to pick another one. And we're going to go through and balance another one using the same 5 steps. So I'm going to go to page 646 in the book, number 12. Okay. The equation we're going to balance is hydrochloric acid plus nitric acid is going to produce HOCl plus NO plus H2O. Okay. So again, we are using the oxidation number method. So step 1, assign everybody oxidation numbers. Okay? There's nobody in here that rule 1 applies to. Okay, so we're going to jump to rule 2, monatomic ions. There are no ionic compounds here. Okay, so now we go to step 3. Hydrogens plus 1, plus 1, plus 1, plus 1. Step 4, the most electronegative element gets what it wants, which is why this HCl, the chloride's -1, gets what it wants, which is kind of rule 5 as well. Oxygen is stronger than nitrogen, so it gets -2. Oxygen is stronger than chlorine, so it's -2. Oxygen is stronger than nitrogen, and this oxygen gets its -2 to make water. And the last step is go figure out what the last atom must be. So nitric acid again, -6 for the oxygens, +1 there. So the nitrogen's +5. Over here we currently have -1, but the chemical's neutral, so the chlorine is +1. This nitrogen must be +2. And we have step 1 all done. You've got to be able to do this quickly and accurately because this is going to be the jumping point for the rest of the problem. Okay? Second step, identify oxidation and reduction. Okay? So you got to look at the thing and figure out who's going up. This chlorine is going from -1 up to +1. So it's being oxidized. Okay? The nitrogens are going from 5 all the way down to 2. So they are being reduced. Okay? And normally it's easy to do steps 2 and 3 together. I almost did that. Okay? Determine the electrons being oxidized and reduced. The chlorine's going from -1 up to 1, so it's 2 electrons. The nitrogen is being reduced from 5 to 2, which means it's being reduced by 3 electrons. Okay? And just like we did way back when we did ionic compounds, the first thing that should pop into your head as soon as you see a 2 and a 3 is that the common denominator is 6. The common denominator is 6, which means we need 3 atoms to get to 6 electrons, and we need 2 atoms of this to get to 6 electrons. So what that means is you have to put a 2 here to get 2 atoms of nitrogen, and a 2 there to get 2 atoms of nitrogen. So these nitrogens will now lose 6 electrons, gain 6 electrons. And we need 3 atoms of the chlorine, so we got to put a 3 there and a 3 there. And now these 3 chlorines will lose 6 electrons. And so step 4 is done. And the last step is to balance everybody else. So you just got to go through and see, did we scoop up any additional waters or what's going on? So we currently have 5 hydrogens on the left. We have 3 hydrogens here and 2 more there. So we have 5 hydrogens on both sides. The oxygen is the tricky one, so let's just make sure we're good there. We have 6 oxygens on the left from the nitrate. We have 3 in the first chemical, plus 2 in the second chemical, plus 1 in the third chemical. So we did not actually need to do step 5, because that was the only chemical that we could have put a number in front of, and it was already balanced. Okay? It seems like a ton of work, and if you just look at the final product, it does look really, really, really messy. But every step along the way is a basic, simple step that we can do, because we've been practicing each step all year long. We're just now putting it together and doing every single step at the same time. Okay? So this is the oxidation number change method. And you just have to do these steps over and over and over and over again until you get really quick and really good at it. Alright, the final section in chapter 20 is how to balance redox reactions using the half reaction method. So the last time we went through the oxidation number change method, which works a lot of the time, but there are some of them that really the fastest, simplest way is to do this half reaction method. So I rewrote the rules in your book again. I shortened them, condensed them so they're easier to remember. And the book also has you do a couple of these in one step, so it kind of makes you do 2 things in one step. I tried to split it so that it's easier to remember, and then you're pretty much only doing 1 thing per section. Okay, so once you've got those rules written down, we'll be ready to go. Okay, So for step one, we are going to do the net ionic equation. There's two ways you can do it. You can split everybody the way we learned before and cross everyone off to create a complete ionic equation and then go to the net, or you can try to do that step in your head and say, okay, potassium is aqueous on the left, potassium is aqueous on the right. I'm going to ignore it. The MnO4 is -1 and aqueous on the left. There is no NnO4 on the right, so we're going to put MnSO4, aqueous on the right, okay? Which, when this splits, is actually Mn plus 2 and SO4 minus 2. Aqueous, aqueous. Okay? And this SO2 is a gas. And over on the other side there is no SO2. Okay, so we currently have all of our net ionic equation already put together. Okay? So at this point we have done step one. Okay? Step two, write an oxidation and reduction half reaction. This is easier to do if you remember the other definition of oxidation or reduction. So oxidation is a loss of electrons or a gaining of oxygens. So if you look at this SO2, it's going up to SO4. So it is being oxidized. And if you look at the manganese, it's going from 4 oxygens down to 0. So it is being reduced. So these are our two half reactions. Every step we do from here forward is going to be to expand this half reaction so that we can put it back together at the end and figure it out. Okay? So, the next thing we're going to do is we're going to try to balance the atoms and their charges. Okay? Now, what's important on this is you'll notice there's no number I can write on the left and the right side that'll make those two balance. Okay, so here's what we've got to know. Okay, whether this is in water or not, at some point the problem's going to have to tell you whether you're in acidic solution or basic solution. And that's really important. Okay, so on page 652, okay, on page 652, we are doing the practice problem in that giant yellow box. Okay? And it's easier to do acidic, so we're going to assume it's acidic. So here's some tricks. Okay? When it's acidic, you want to add H2Os to balance the oxygens, and then you want to add H pluses to balance the hydrogens. If it's basic, you want to add twice the OHs to balance the oxygens, and then you add waters to balance the rest. Okay? So on this step right here, we're going to assume we're doing acidic solution. And so for our oxidation reaction, we are missing 2 oxygens on the left-hand side. So we want to add enough waters to balance the oxygens. So I'm going to change colors here. Okay? To do step 3, we need 2 waters on the left. And once we balance the O's, we have to add H pluses to the other side to balance the hydrogens. So this has 4 hydrogens on the left, so we're going to need 4 H pluses on the right. Okay? For the reduction side, we're still acidic, so we need to add water to balance the O's. We need 4 oxygens on the right, which means we need 8 H pluses on the left. Okay? We are almost done with step 3. Because we not only need to balance the atoms, we also have to balance the charges. Okay, so to do that, I'm going to switch over to a blue. Okay. Currently, on the oxidation half reaction, the left side is neutral. The right side has a +2 charge. So that we're missing 2 electrons. And if you remember that oxidation is always losing electrons, you can tell if you did this correct, because in order to balance it, we have to kick 2 electrons out. Okay? On the reduction side, the right side is currently +2. The left side is currently +7. And again, the only way to go from +7 to +2 is if you put 5 electrons in. So at this point, we now have 2 completely balanced half reactions. Okay? The next step, which is very similar to the oxidation number change method, we have one reaction trying to bring in 5 electrons, the other equation trying to release 2. Those don't match. So what you have to do is you have to get to a common denominator, just like we've done all year long. So we're going to multiply the oxidation by 5, which will be 10 waters plus 5 SO2s makes 5 SO4 -2s plus 20 H plus 10 electrons. And we're going to multiply the reduction by 2. So we're going to get 10 electrons plus 16 H pluses plus 2 MnO4 minus makes 2 Mn plus 2s and 8 H2Os. Okay. So that is how we balance the redox electrons. Because this one was oxidizing by 2, this one was reducing by 5, so we have to balance them. At this point, we now can combine the half reactions. So just like we did for Hess's law when we were doing heat of summation, we can now recombine these 2 equations. The 10 electrons on the left cancel with the 10 electrons on the right. We have 16 H pluses on the left and 20 on the right, which leaves us with 4. We have 10 waters on the left and 8 on the right, which leaves us with 2, and nobody else cancels. So what we do is we now write our new equation, which has 2 waters plus 2 MnO4 minuses plus 5 SO2s. Oops, that's an S. Makes 2 Mn plus 2s plus 5 SO4 minus 2s, give myself a little more room, plus 4 H pluses. Okay? So we have now combined our 2 half reactions, and we are almost done. The very last step, okay, which can be hard if you can't keep track of things, so I'm going to underline it in black. Okay? Notice how in our original equation, every MnO4 needed a potassium to go with it. So we're going to add 2 K pluses to the left, which means we have to add 2 K pluses to the right, which is lucky for us because the 2 K pluses needed to go with the sulfates. Okay? The other thing we should notice is that we can now put together, we have 2 waters. We now have 2 KMNO4s, and we have 5 SO2s. Okay. Over on this side, we have 2 Mn plus 2s, but in our original equation, all the Mn's were stuck to sulfates. So we're going to steal 2 sulfates away to make 2 of those, which drops this to 3. We're going to use 2 of our K's to steal one more of the sulfates away to put our original equation back together. And now we have 2 sulfates and 4 H's, which, luckily for us, is exactly 2 sulfuric acids. And which gets us to our fully balanced electrochemical equation. Okay? We are going to do one more of these in basic solution. Okay? The basic solution one is the same sequence of steps, it's just you have to add OHs instead of H pluses to it. Okay? So you're going to want to watch this video a couple times and walk yourself through it and follow along so that you can understand how to do it, and then next we're going to do it in a basic solution. Okay, so I just erased all the stuff we did after this step on the last one. So now we're going to work our way through and we're going to balance this equation using, instead of an acidic solution, we're going to do it in a basic solution. So the first step is still the same. Get your net ionic equation, which we already did in the last part of the video. Okay? We're also going to write our oxidation and reduction half reactions, which are the same. So again, I'm going to redo this for you so we can pay attention. So the manganese is losing oxygens, which means it's being reduced. Okay? And I'm going to give myself lots of room, unlike we did last time, so that we can start building things. Okay? Oxidation, the sulfur is going from 2 up to 4. So the same reason why it was oxidized before is the same reason why it's being reduced now. Okay? And then this is where this piece of information becomes important. It's right here. Okay? If it's a basic solution, if you remember from before, we will always want to add twice the hydroxides to balance the oxygens, and then we can use waters to balance after that. So for our oxidation half reaction, we need 2 oxygens on the left, but we need to add twice as many as that. So we're going to add 4 hydroxides. And by doing that, we now have 4 H's, which is going to be 2 waters. Okay? That balances our atoms. So we now have 6 oxygens on the left, 6 oxygens on the right, 1 sulfur, 1 sulfur, 4 hydrogens, 4 hydrogens. Our atoms are balanced, but our charges are not. So currently the left side has -4, the right side has -2, which means we need our 2 electrons to come out on the right hand side. And you'll notice that's the same number that we got when we did it in an acidic solution. Okay, so now we're going to do step 3 for the reduction half. We have 4 oxygens on the left, so we need to add 8 hydroxides to the right, which allows us to write 4 waters. So our atoms are now balanced. So this balances our atoms. And now we need to balance our charges again. If it's truly reduction, then the electrons have to go on the left-hand side. The right side is -6. Currently the left side is -1. So again, we need our 5 electrons. Notice how this and this are the exact same number for the acidic solution and the basic solution. Okay? Which is why we, when we do step 4, need to multiply the oxidation by 5 again, and we need to multiply the reduction by 2. So now we have 20 OHs plus 5 SO2s makes 5 SO4s plus 10 waters plus 10 electrons. We get 10 electrons plus 8 waters plus 2 MnO4 minus makes 2 Mn plus 2s and 16 OH minuses. This gets our 10 and our 10 equal, so we can now combine them. The 10 electrons on the left and the 10 electrons on the right cancel. We have 20 OHs on the left, 16 on the right, which leaves us with 4 on the left. We have 8 waters on the left, 10 on the right, which drops us to 2. Then from here, we just add everybody down. And again, I always try to put everyone back where they were in our original. So I'm going to put the 4 OHs out in front. We then have 2 MnO4 minuses. We have 5 SO2s. And over here we have 2 MNs, 5 SO4s, and still have 2 waters. Okay? And now for our last step, adding our spectator ions back in. Okay? Oops. Which over here, again, I'm running out of space. Every MnO4 down here had to come with potassiums on it. So we're going to add 2 Ks to the left, which means we have to add 2 Ks to the right. And every Mn here came with an SO4. So again, we're going to steal 2 of those, which drops us to 3. Then we're going to put our Ks onto that. So we have 2 K2SO4, which drops this to 2. Okay. Plus 2 H2Os. This side, we now have 2 KMNO4s, 5 SO2s, and here's the trick. Okay? We still have 2 SO4s over here that we haven't accounted for, and we still have 4 OHs on the left. Well, these SO4s could easily make more sulfate K2SO4 as long as we added 4 more potassiums over here. Then we can change that to a 3. And if we add 4 more potassiums on this side, then we get 4KOH. And we have now balanced our chemical reaction. Okay? This method takes some practice and some getting used to. It's a lot of work. You've got to practice it, practice it, practice it. Every time one of your problems in the book says, solve this using the oxidation number change method, if it was me, I would practice it that way first, and then I would do the half reaction method and make sure that you can do both as quickly as you possibly can.